Welcome back. Please do pardon my earlier attempt at trying not to lose my audience. So we are back with the same number that we had before going for the tea break. So welcome back. I'm sure you're all looking forward to being a part of this discussion. Near space and space sovereignty. As I shared earlier, DevSat has many firsts, and a discussion on near space is amongst them. Let's start with inviting the esteemed chair and moderator for this session, Air Marshal G.S. Bedi, AVSM, VSM, retired, former Director General FIS, distinguished fellow at CAPS. May I request the esteemed chair to please join us on stage. Also joining us for this session, our esteemed panelists are as follows. Air Vice Marshal D.V. Khot, retired, former DSA and fellow CAPS. Mr. Pawan Kakkar, Managing Director, Jugapro India Private Limited. Group Captain T.H. Anand Rao, Senior Fellow CAPS. And Mr. Sameer Joshi, Chief Executive Officer, New Space Research and Technologies. A very warm welcome to the esteemed chair and the panelists of this session. So I now hand it over to the esteemed chair. It's over to you, sir.
Thank you very much. Good afternoon, ladies and gentlemen. Now this gathering, nearly reminds me of near space, the presence in near space. And we were wondering that, at this time of the session, invariably you will have more people on stage than in the audience. But my compliments to you, because I guess this is the real serious audience, who want to know something new and something different. Now, I will just start, because I will keep introducing the panel as and when I get to them. Near space is actually generating a lot of interest now, and incidentally in the India Space Congress of 2022, okay, we discussed this near space issue, where I itself along with Khot and General Panu, we had touched this subject of near space and fantasized about what all can be done in near space much before Chinese balloon appeared in the US skies. Now after that, it has made it almost synonymous with household things, that near space and balloons have started getting discussed. Okay, now this near space was definitely used to transit to space, okay, but there wasn't much presence in this segment. Now, was it neglected or was it ignored? Probably yes, but not really, because there wasn't any intent, or owing to lack of intent, but it was more owing to lack of capability, I would say. Now, traditional aircraft that we are used to have influence at the most, let's say, up to 20 kilometers, if you are not getting into fractions. I mean, including their weapon launch and their effect, because even F-22s had to wait for that balloon to descend to certain altitude before they could really target it. Okay, but why they are not going above 20 kilometers? Because there isn't much atmosphere there to produce enough aerodynamic forces which can sustain flight. And the higher you go, the faster you have to fly. For example, SR-71, flew at almost 85,000 feet, but had to be at Mach 3 plus at that altitude. But those were the days when satellites, etc., were not so much in vogue. and surveillance or intelligence had to be gathered by those means. But it was Herculean task. It almost took an army to prepare that aircraft, and for the purpose of statistics, 12 aircraft out of 32 were lost owing to mishaps, because either some accidents or some malfunctions, etc. Not a single one to enemy action, but 12 out of 32 were lost. So it won't make sense probably in modern times to make that kind of platform just to venture in that space. And if aircraft couldn't be there, above that altitude, then why couldn't satellite come down? Now, satellite also couldn't be in that space for two reasons. Because ironically, if for the aircraft there is too much atmosphere there, I mean there is not much atmosphere there, for the satellite it was too much atmosphere there. It isn't used to operating in that kind of atmosphere. And if a satellite, second reason is, has to go around, let's say we are talking of space below 100 kilometers. If a satellite had to sustain itself in an orbit at that kind of altitude, okay, let's leave the drag for a while out, it probably has to rotate at a massive speed. For example, a satellite at geostationary in a orbit which is rotating at the angular velocity of the Earth, rotates, given the altitude of 36,000 kilometer added to Earth's radius, at about 3 kilometers per second to have the same angular velocity that of Earth, so that it remains at a same point. Same thing which comes down to about 400 to 500 kilometers, virtually about 7,000 kilometers of radius or 7,200 kilometers radius from center of the Earth, has to go around almost at 7.5 to 8 kilometers per second. So now you keep coming down, but at these altitudes what happens is there is nil atmosphere, there is no drag, the Mach number effect does not come really into operation, or it's not really relevant. But if you were to come to a place where there was atmosphere, then satellite at that speed, probably 10 to 11 kilometers a second, will have to rotate, with very high speed, just to draw an analogy, because satellite has to produce centrifugal force to stay in orbit, which balances the Earth's gravity, like a hammer throw, with a 8-pound hammer throw with, let's say, 3-meter string attached to it. If I can rotate at a particular speed and it goes to a particular distance with that force, if I, 1/4 the radius of that string, you can imagine how fast you'll have to rotate for it to reach the probably same speed or produce that kind of force. So with that, it was not possible to operate satellites there. And there was another underlying reason, that if 100 kilometers was supposed to be a sovereign space, then you can't have your asset going around over other countries, below 100 kilometers over sovereign space. It will be a regulation issue. So because of this space, we can say, remain neglected. That we did not have capability, nothing much happened there, only weapons transited that place, etc. But now with new advent, we are building up capability. So now we want to be in near space. But why do we want to be in near space? It is, to achieve something or enhance your capability. No, but they cannot be looked in isolation. We already have capability in lower space and we have in upper space. We have all seen that. Okay. So capabilities developed in near space will have to be integrated with these two segments. So primarily we are looking at three issues that emerge. One is capability, the capability that it takes to be there, and what capability comes out of it, both combined. To the regulation, that how do we make the regulations for these assets to be there, because there are going to be other assets there as well. And the integration of now all the assets that we place in lower space, near space and the upper space. And also not to forget the civil application. Since morning we have talked about that military, civil, etc. Now I look at it like this, that for any military technology to thrive, it must have a correlative civil application, or for this to thrive. For example, just imagine if aircraft were only military, there were only military aircraft and no civil aircraft, I don't know how much aviation would have really progressed. Or if the space application was only military application without any civil application, today the number of communication satellites is probably 10 times more than ISR satellites. So their civil application has to be thought about along with it. So now to discuss all this, we have a panel of distinguished speakers with me comprising military and industry, and I'll introduce them briefly as I invoke their intervention. And to begin with, I would like to, in space language, to say launch Mr. Pawan Kakkar on my extreme left. Mr. Kakkar is the CEO at Jugapro India Private Limited, and Jugapro has been observing the emerging changes in the lower airspace, in particular with respect to drone space. Now, Mr. Kakkar, I would request you if you can, touch upon these aspects briefly in about 10 odd minutes. Okay, we have the good fortune of having few speakers. The topics I want you to discuss is that how can we harness the intelligence being collected by legitimate drones owned by multiple agencies and public for the benefit of security agencies? What is the collaborative model which can help the drone ecosystem grow in India? And where should the industry focus in terms of collaborations and compliances? And not to forget, ever-present challenge of differentiating between legit and rogue drones and the traffic management thereof, so that we do not lose out on the capability just because we cannot manage it. Over to you.
Thank you very much, sir. Quite a task. From ground, I have to reach the space. So Samir has already soared the heights of space. I'll stay grounded, pun intended. We'll be talking of small drones. We'll be closer to ground, so we are not talking of kilometers, we are talking of hundreds and thousands of meters. The challenge, what has been thrown in this particular lower airspace is omnipresent. So it addresses all the spheres of space now. As sir said, that the civil aviation has to take off. There's a launch. So the drones are a threat to air bases, all the assets that we have built on the ground. So can a multi-billion-dollar investment be put at risk by a $200, $300, $500 drone? That's one aspect that I'll touch upon in the last. But let's look at what the drones can do and where we are and what is the advantage the industry in India has in the drone ecosystem. The biggest advantage that our government understands that the drone ecosystem is one of the fountain heads of growth in the global arena. We can put drones into multiple applications, going right next to the satellite and onto the agricultural field. Nowhere this kind of a penetration, the fast penetration has happened in this industry across the world. So we are a zero to hero country, and taking that advantage, what can industry do to talk about all the challenges which sir mentioned? So can we talk? So drones have to talk to ground, and the drones have to make satellites talk to the infrastructure on ground where the footprint doesn't happen. So that could be one use case which is very, very pertinent to this particular August gathering, that do we have a satellite communication? Can our drones extend the network to an advantage of our defense forces where we do not have a footprint? Can drones be a part of a communication network? So I'm not talking of pizza getting delivered. So if you are keeping your door open in your balcony, I'm not looking at that particular aspect because you are wondering about your dinner also. But what does a drone deliver? So if there's industry segment here listening, are you solving a real problem? Are you relevant? Because the funding winter is here, it might stay longer. So collaboration, we have talked about collaboration, is the key. If there is a solution, why invent the wheel? Put it on your aircraft, make it spin. So we'll have to evaluate. That's where this forum, other forums, and we are very, very happy that defense ecosystem is talking to the industry and academia in a closed room. I have just suggested, General Man, that please open one of your conference rooms in one of the buildings where we can bring in our computers, we can walk in, and we can give you some presentations. So that industry collaboration between industry and academia, between industry itself is very, very important. The problem I see with drones as a challenge is what if it falls on my head? We are absorbing the technology faster than we understand it. Just because somebody else made it, I can also make it. It's not cut, paste, and copy. Some of you would have been spending, how many, maybe a decade? And he's just taken off the ground. Whether he has made money or not, I don't know. But there'll be a lot of us who will like to copy his success. But drones falling on your head from few hundred meters, few hundred feet, are a projectile by themselves. Do I need to load any ammunition on a drone? If I can just drop a 5 kg, 10 kg tattoo battery, it might start a fire. So we could be talking of Aramco again. But then another aspect that we have to talk is the vulnerability of our communication systems. When we are talking of encryptions. How does my drone talk? Is it encrypted? No. 99% people who understand anti-drone systems understand spoofing. They understand that you can make a drone land by doing spoofing. What if my adversary spoofs my own target, my own property as a target, and brings down a drone on my head? I am looking at a huge swath of land. So when you pick up a camera in a military airbase, you can't click a photo. But you can fly a drone 4 or 5 kilometers away and you can collect a lot of information. Who owns that information? Does government have an authority to dip into that particular information lake? Somebody mentioned about information lake. So the collaboration is that all the drones which are up in the air, they're collecting some information. Is that information a sovereign asset? That's a question we are asking in US, because there my airspace is my asset. So any information about my head is my asset, not your asset. So if you come into my thing, it's a criminal offense. So what is that data? Can you stop that data from going out of the country? When you are flying a DJI, it's suspected that you are putting thousands of eyes up in the sky at your own expense at somebody else's benefit. Since it's a very late evening, I'll rest the discussion here. I'd like to introduce what we do. We are an anti-drone company. So if pizza is not coming to your house soon, we are the guys. We are jamming that from the protected area. So we can protect a 2-kilometer radius with about 80-85% efficiency. Almost all non-military drones will not enter. How? I'll not do it here. I'll leave it for the next time. Thank you.
Thank you, Mr. Kakkar. Some interesting observations. Now, drones definitely have become a household name. Shahid in Russia-Ukraine war has almost become a household name. And a very good observation you made, that are you really solving the problem, or are you solving the real problem, and are you relevant? These are the questions every innovator or everybody who makes anything has to ask oneself. And we are absorbing the technology more than we can understand it. It is for professionals to see that. Thank you very much for your intervention. Now, next on the line, I have Group Captain T.H. Anand Rao on my right. He is a senior fellow at the Center of Air Power Studies, New Delhi. He is a keen observer of the space domain. His area of interest is space security and policy analysis. He has written many papers and articles on issues concerning space security. He has authored a book titled India's Space Security Dilemma, which was released in 2021. And his present topic of research is space domain awareness. Now, Rao, we all know that long-range weapons, always transited through this segment, but then there wasn't anyone else there generally. But now, since we are talking of other regular assets habitating this segment, and since space security and policy analysis is your expertise, would you please throw some light on peculiarities and challenges arising from near space operations in terms of regulations and the emerging operational issues like traffic deconfliction and air defense? Thank you.
Thank you, sir. And good afternoon, everyone. It's indeed an honor to be part of this esteemed panel. After listening to the drone environment by Mr. Kakkar, I will take you to much higher altitudes, to what is commonly being known as near space. And to look at this near space region, I think there are three primary issues which we need to look at. First is the demarcation itself, and the sovereignty issues. The other is the exploitation of this region, for which we have experts on this panel. And the third is the traffic management issues in this region. So I'll cover the sovereignty, demarcation, and the traffic management issues. So there are two questions which occur to my mind. Firstly, why is near space being called as near space? And why is 100 kilometers the limit for the beginning of space? So near space is actually, in fact, both these terms are not internationally accepted terms, and Dr. Anjana will agree that these are not legally accepted terms. So these are only terms of convenience that we use. And convenience because we want to operate in this region. So the Americans started calling it near space to operate and exploit the utility that this region has, because the moment you attach space to it, the sovereignty goes out of the window. And that's why near space term is being utilized. That's my opinion. But then this is not the correct terminology. It's actually the upper atmosphere. And when we look at the Chicago Convention of 1944, it says that sovereignty exists in an airspace, and airspace extends up to the limits of outer space. Now, though that definition may look good, but there are some problems with that, because neither has Chicago Convention defined up to what limit the airspace should extend, and neither has the Outer Space Treaty defined what would be the beginning of space, and therefore we have a problem. So what we follow as the Kármán's line, or 100 kilometers, is the generally accepted norm, but again has no legal sanctity. If we look at the documents of how the Kármán's line was formed, there are a number of calculations which actually suggest it's somewhere closer to 80 kilometers. But okay, some people follow 80, some people follow 100. But the fact of the matter is, this is again, there cannot be a distinct line to define space. And there are a number of people who have worked on this issue and come up with many theories. And primarily three theories stand out. One is that airspace should extend up to the limits up to which lighter than air vehicles can go. And the second theory, which says that space should start at the lowest altitude at which satellites can orbit. But in both cases, there is clearly one region where nobody operates, and that is roughly between 50 and 150 kilometers, where nobody can operate. Maybe in future technology may improve and we might find some lighter than air vehicles operating in this region also. So this should be something like a buffer region between airspace and outer space. If we stop thinking of near space as space, half of our problems of regulations get resolved. But since we are calling it near space, there are issues because the regulatory mechanisms are not coherent in both these mediums. So that's the first issue. The other thing I'm going to talk about is the traffic management issue, and here there are again going to be problems because all these lighter than air vehicles which are going into this region about 20 kilometers, or let's say above flight level 60,000 feet, which is the limits of Class A airspace. These are all dual use vehicles, dual purpose vehicles. And if it's dual use, we actually don't know whether it's a covert operation or it's a civil operation or it's some commercial vehicle. We don't know. And therefore, controlling this traffic in this region becomes a real problem. And also because some lighter than air vehicles like balloons are relatively easy to launch them compared to an aircraft. There are problems associated with that too, which I'll not discuss here. But balloons are relatively easier to launch, and therefore there are a number of amateur operators who are launching balloons today. We don't know, I mean, we just heard about the Chinese balloon being shot, but actually that's only the tip of the iceberg. There may be many more balloons operating in this region which we don't know about. And therefore, the question comes of the surveillance mechanisms in this region. What kind of surveillance mechanisms region? And all these vehicles which go up have to transit through the controlled airspaces, which are Class B and Class C airspaces, which could be restricted or unrestricted airspace. They have to transit. So what kind of mechanisms do we need for this? There have to be regulations for that, which do not exist for the upper atmosphere. The upper atmosphere is also called as upper class C airspace, which is an uncontrolled airspace. The next issue would be surveillance I talked about. There are large gaps in surveillance because it's not only the vertical extent to which we can see, but also there are gaps in the horizontal geographical span of coverage of radars, and therefore there are vast swaths of area which we cannot see in this airspace. Therefore, surveillance mechanisms also have to catch up. So what do we do if these near space vehicles are operating in own territory? It's relatively easier because it's probably known that this aircraft is there. There would be mechanisms of flight plans and NOTAMs being issued. But most of these, which are the aircraft which are operating in this near space, are going to be for military purpose, and therefore they have to go over enemy territory. And therefore there's another problem which arises, that is of the threat perception to these, and therefore these vehicles have to be built survivable. They have to be made survivable. And there is a need for enhanced surveillance, which I would call as near space awareness, something similar to space situational awareness. These are some of the things which need to be worked upon. And lastly would be the how can the industry help in coordinating this traffic? Improving this traffic management. That is, products such as high altitude platforms which could act as radio relays, high altitude platforms which could have radar payloads, which could help in seeing the traffic below them. These are some of the things which can be worked upon. And lastly is the issue of air defense. Now, air defense of this upper atmosphere, which we are calling as near space, obviously has to be with the Air Force, since it's a sovereign airspace. And therefore, to carry out surveillance, to carry out the air defense in this area, the primary requirements would be that of having adequate surveillance in this area, traffic control through procedures which are adapted to this area, because the procedures which currently exist only cater to the altitude bands in which the aircraft would normally fly, which is up to 20-25 kilometers. And then for air defense also, the weapon systems will have to be developed for engaging hostile high altitude platforms in this region. And the launching missiles or ASAT weapons for engaging these would not be cost effective, and therefore there will be a requirement to have air launched weapons to engage hostile platforms in this region. As far as integration is concerned, it may not be a good idea to integrate entire airspace with space, but what we require is integrating the usable airspace with the unused airspace and maybe some portions of the suborbital region for continuity of operations. With that, I rest my case. Thank you.
Thank you. Thank you, Anand. And typically, nothing much to say on what he said. His research is profound, and his statements are obviously nothing but the truth. And like he said, I've just reminded when he mentioned Chicago Convention, that in which they try to define space, but neither lower space was defined nor upper space was defined. Okay, typically as a convention, and I just remember one line about a committee. Somebody wanted to define committee, and he said, camel is actually a horse designed by a committee. So it's generally these things end up doing such things. Okay, thank you for your intervention, Rao. Now next, we have Samir Joshi with us on the extreme right. He's the CEO at New Space Research and Technologies, a very successful entrepreneur, and has done great work in drones and swarms. Those of you who were here last session must have heard General Brar mentioning about it. also been an accomplished fighter pilot in the Indian Air Force, and I have had the privilege of operating with him in Kargil operations. We both have taken part together from Srinagar from the same squadron, that is 51 squadron. And Mr. Kakkar put a doubt in my mind when he said, don't know whether he has made some money or not, otherwise I had come with an application in my pocket to new research technologies. Joe, now no one can be better qualified to tell us where does the Indian industry stand in realizing the capability in near space, and what are its challenges now, and how can academia or the military help in growth, because I believe you are venturing into this domain as well now. Thank you.
Thank you, sir. Very kind words and a rush of fond memories also, but no time for that. Good evening, ladies and gentlemen. It's a real privilege to be here. I'm Samir Joshi, CEO at New Space Research and Technologies, and we happen to be one of the companies who are working in the field of new space stratospheric platforms. Just to continue on the pun what Marshal Bedi said about near space, the government first time saw a proposal for a near space R&D air vehicle back in 2017, and the first sanction for a very baseline R&D program was given in 2021. So that is how near the near space is. So, before I tell the industry perspective, it's very important to understand how where we are, and why near space is being spoken about. The lower space, we have multitude of civilian and military tasking. The military taskings revolve around certain what we call as air-launched effects, ALEs, and these can be through manned platforms. These can be through unmanned platforms. There are a host of services which are being given also in the civilian side of the community there. Similarly, for the satellite side, again, we have satellite-based effects right from the inception, largely dealing with surveillance. But there are a lot of new niche functions which we are not aware of. And on the military domain, there's a lot of hush-hush functions, which finally, which at times come in the open. But especially since the mid of 70s, a lot of functions in the military space, especially in low Earth orbit, and probably to an extent in the geostationary orbit, have been very, very evident. Now the issue here is when, again, I'll start from the military standpoint first. When the military planner went down to the board, he realized that the effects which are being created by the lower order drones or the lower flying drones are not enough. He needs to see more. He needs to listen more. He needs to have a better perspective, more situational awareness. While the effects being created in space, in low Earth orbit, while they're good, a lot of persistent, but they cost a lot of money. And here comes, a solution sometime in the middle of 80s when, technology started to open up for two different vectors. One vector was, pivoted around the lighter than air objects, primarily airships, balloons, blimps, which have been there for a very long time, but people were finally able to take them very higher. And the second effort was based around solar-powered UAVs, which could stay for a very long time in the air. Of course, it took about 20 years before a very advanced drone like Zephyr could reliably, the Airbus Zephyr could reliably prove a point and say, yes, a drone can stay in the air at stratospheric altitudes of 17 to 20 kilometers for a very, very long time. And this is, I'm talking of a multi-day flight. Mind you, it has just, in fact, last year it broke the world record set a world record of 60 plus days in air over proving grounds back in the US, in Yuma. Similarly, there were efforts, a large number of efforts for lighter than air platforms, especially blimps. There was a big effort from Google for the Loon program. Of course, it did not materialize because of other things. The balloons were able to go up, stick between 17 kilometers to 18 kilometers above mean sea level, and beam down, things like internet. But the cost of kind of ownership as well as the acquisition just did not materialize. So Google kind of shut down this avenue. Then what actually happened is that a lot of countries, they took a serious note, okay, should we go balloon or a blimp or a airship way, or should we go for a UAV way? So there are a lot of advantages, which are technology-based advantages, which are operational advantages. Again, advantages and disadvantages. And it's starting right from managing helium. When you take it up there, it becomes a very, very dangerous gas. Not many people can kind of keep it right up there at stratospheric altitudes. To kind of getting these lightweight UAVs where the structures are so light, they get into rampant oscillations, and finally the structure breaks because of aeroelasticity effects and a lot of environmental issues. So this kind of degradation happens for this class of vehicles. It has been spoken, the environment in stratosphere is very tough. And this is where it kind of all circumvents to. I forgot to mention effort in the airship side is a platform called the Stratobus from Thales. It is still underway. So these are very functional kind of near space stratospheric vehicles which are there right now. But to be very frank, if somebody is wanting to put money on any one of them, no, right now it may not be possible. We have not achieved that junction. Airbus is just about at the juncture of kind of starting to commercialize, or it's in the market to commercialize this activity through a company which is set called Alto, and they want to stay somewhere near the equator. So I'll go back a bit before I get down to what we are doing. I want to give you the baseline technologies which are very much required, to get these vehicles cracking. A lot of development happened, and I'll focus more on the UAV side on lightweight structures. Now what happens when you go to stratospheric altitudes? The density is literally next to negligible. The air is very thin. To keep a platform right at those altitudes, you need to create a lot of lift, you need to generate a lot of power. And towards that, excuse me, and towards that, there is a need to being very light. Being light means getting to very exotic material space, carbon fibers, even the different types of carbon fibers. And this is where the research has been going in the last 30 years. Then the next exotic tech about this is solar panels. Solar panels which can give and stick on the wing, can give you a platform where you can still maintain your lift, and do not add to the drag, and it's all about aerodynamics, etc., while getting enough sunlight, converting into power, one, to run the vehicle, and second is charge its battery, because it has to survive through the night again on batteries only. So this is the kind of the quantum of solar panels which we are talking of. And as you start to come close to the Earth, the density, the efficiency of the solar rays, it reduces. Mind you, this would have been piece of cake right in low Earth orbit, where at 600, 500 kilometers, you have enough sunlight, you have enough things to charge that. Then the next revolution happened in the field of batteries. Obviously, we have to fly through the night. And to do that, you need to have very high energy densities. And the industry actually focused. There were leads like Airbus again, and the ecosystem around the UK, which kind of came up, and this thing went back in the US. A lot of path-breaking technologies around battery tech, which could fly right up in the stratospheric altitude in a very harsh environment. Mind you, temperature is as much as minus 60 degrees. There are, even the minuscule amount of winds out there kind of take a lot of effect. So the batteries, whatever energy density, we are talking of right now the Zephyr, the Airbus Zephyr is flying close to with about 450 watt-hours per kg. These are the kind of densities. And there are new chemistries coming out like lithium sulfur. All of us, we look very keenly at what's happening in the electric vehicle space, and we kind of, study that space very, very evenly. But I can tell you right openly, none of those batteries being used there can be taken up in the air. That's a totally different domain. And that is what makes it more difficult. And, beyond this, of course, the communication, how do you communicate so effectively for something flying right up there at 20 plus kilometers? Similarly, you need to design very specific BLDC motors, because as you go up, the petrol engines just won't work. You have to have your electric propulsion, and that is the only source, even for airships, as well as for the UAVs. So this is another very, very niche area as we start to go up. So when we kind of traverse this, when we kind of go on this trajectory, one thing clearly stands out. And that is the cost of ownership. Not the cost of ownership, the cost of design and development. And that is the reason why very few countries in this world are kind of putting their weight around these kind of efforts. And I mean, we in India are just about starting this effort in a very serious way. Of course, like a lot of things which have happened in the past, military is taking the lead, but cost is a big prohibitive factor. And it is also a reason why, the failures, and which are bound to be more in such a harsh environment, may not be tolerated to that an extent. So all these things, kind of we as an industry notice. A company like ours, while our core is also swarming, but we are into persistent robotics, and the HAPS, the high altitude pseudo satellite, is a genre of vehicles which are emerging around the solar powered UAVs. Why they are called HAPS is because they can do about 70 to 80% of functions which a satellite can. So that's where the word pseudo is added. Also, for the auditor, if you call it a HALE, he will say, no, we already have a HALE, so we'll not allow it to develop. So that's another way. Maybe that's how it came up, but it worked very well in India also, when we were right at discussing how to take this forward. So New Space Research and Technology is based out of Bangalore. We have an IDEX program which we are about to finish. It's kind of a spiral development for a platform which we aim to take it to the stratosphere. The first year is something which we are flight testing. The last flight on the winter solstice was at low levels of about 3.5 kilometers AMSL, which was the mandate of the test, and we could fly about 21 hours. On the summer solstice, we'll be aiming to fly 2+ days, which is again the mandate of the program. The next spiral development will target about 7 days at stratosphere level, and the last is going to be, which is now coming up through a very big Make One program. We all know what Make One is all about. It's a largely government-funded institutional effort where the major chunk of the money comes from the government of India. And because we're talking of thousands of crores probably in development of this class of vehicles. So that is going to aim for a solar-powered UAV which will fly at 20+ kilometers for more than 90 days. This is the impactful capability where we are looking at. And why this is very significant? Straight away, this can augment the large gap between the data needs and data actually reaching, for persistent surveillance. We have satellites. We are doing a lot to cover the gaps, but it will not be enough. Plus, it's going to cost. The cost of a HAPS class of vehicles is about 1/4 the cost of a satellite of an equivalent grade. And the best part is it can go up and come back. You can change the payload. You can send it again and again. There is going to be a cost of maintenance. But the flights, if we look at a global hawk, which can also fly in the stratosphere, it costs about $100,000 per hour of flight time. What we are looking at a HAPS class solar powered UAV, it's $500. This is a stark reminder. Obviously, the military connotations, of course, Khot sir will cover. But the fact of the matter is, there is too much to gain and too much to miss if we don't try to give it a serious shot, to give it a serious effort. And that's why it's very important for all end users, starting with the military, because the military can afford this cost. The military is something which has a need, a latent need for a platform, starting with ISR, communication relay, and the kind of things. We are at the cusp of, a status quo where anything which can be layered up to kind of increase the overall coverage in terms of the situational awareness is a bonus point. And data is the next oil. Data is something which, right from our troops, everybody consumes. The civilian connotations are not to be missed. Imagine a platform like this beaming down internet right from the skies. Imagine a lot of cell phone towers, especially going into 6G technologies when they're going to come. You don't have to replace the network again and again. Just, taking the full latency on these class of platforms. Imagine these flying towers in the sky. I sold the same story back in 2017. I'm trying to sell it now also. But the main effort, the main vector of operational use will come through the military. And before I close this little discourse, my only request to my end user is, so please be patient. This is not a normal class of UAVs we are talking of. This is something where we will have to fail a lot to actually reach a level where we feel that we will be at par with a technology development effort of a similar nature happening in the world. This is one of the technologies where we have, as a country, caught it at the right time. We are not very far from the international partners, from the players, and I think this is going to be a huge, huge bonus for all of us in India. And if New Space or anybody who's in this space kind of succeeds, it's going to be a huge win for all of us here. Thank you.
Thank you, Samir. You not only covered peculiarities and challenges, I think you very decently summed up why we should have been having this session at all. Okay, thank you very much for that, and I'm sure people will take note, and this recommendations of this conference go up to a very high level, and this will form a part of it. Now, the last speaker on my panel, we have Air Vice Marshal D.V. Khot. He's recently retired from the IAF from the post of Director General DSA, Defense Space Agency, that is, and he's participated in such forums extensively as the DGDSA, and thus it makes his presence today extremely relevant. Khot, a fighter pilot by profession, has many firsts to his credit, starting with being first in his course, a proud recipient of the Sword of Honor. We must give away a round of applause. And then being the first instructor and examiner in the United States Air Force to be deputed from the IAF. He's an intelligent and extremely knowledgeable officer, so I wrote once in his annual confidential report. Near space, can also support military applications other than ISR, like communications, space situational awareness, and countermeasures. Space between aviation and LEO zones, hitherto a largely unoccupied transit zone, is now seeing possibilities of prolonged presence, as we have just heard. But the question is, what capability is required to realize that, and then what capability comes out of it, like I said in my opening remarks as well. Now, Khot, I would request you, if you could elaborate on the enabling technologies, the capabilities, both military and civil, that can be drawn from venturing into near space, and the challenges in integration across various altitude bands. Thank you very much.
Very good evening to everybody from SI here. Thank you very much for the invitation to participate here. Dr. Bowlery, General Pannu, Mr. Prakash, St. Joe's, Dr. Sir. Thank you, Chair, for the introduction, and my co-panelists. And very competently covered several points here, which is going to make my portion simpler. To start with, why near space? And then, as Group Captain Rao very clearly brought out, what is near space? It's an area which has been ill-defined, variously understood, and still not, it still defies quantification. But I believe that there is some thought required to be given to the various zones as they obtain, because the characteristics of the upper atmosphere change in very significant ways, and that alters the manner in which you might exploit it. It changes the kinds of technologies you need to exploit it, and how you may operate in it, and what you may extract from it. And therefore, some sort of clarity on zoning is necessary, so I'll just spend a minute on that. This is my own kind of prescription or offering or understanding. We know the core aviation zone is about flight level 460, airlines fly up to there. That's about 14 kilometers. Combat aviation bumps it up to maybe about 20 kilometers or so, about 60,000 feet or thereabouts. But that's again kind of limits whether it's the HALE class of UAVs, drones, or whether it's fighter aircraft. Above 20 kilometers and to roughly about 30 kilometers was specialized aviation. Aircraft like the MiG-25, the SR-71, the U-2. Some of them crossed that altitude. But that was a rarity, and those are exceptions. Beyond that, really speaking, no fixed wing aviation. Now that's the balloon zone thereafter. Where have balloons gone so far? The highest sustained altitude was touched by a NASA balloon, about 48.5 kilometers for of the order of several hours. The all-time record is 53.7 kilometers. But that was, they touched that altitude and then the balloon descended. So the core area for balloon operations is probably somewhere between 18 to 37 kilometers, where it may be attempted with a certain amount of reliability, predictability. So what we have here is aviation largely below 20 to 30, depending on how you look at it. 30 to 50 balloon zone, that's about the stratosphere. We really don't have a solution for the layers of the atmosphere beyond that. There's a mesosphere, ionosphere, and so on, until we get into orbital space. So it's a transition zone. Things transit through it, whether upwards or downwards. With the HGVs, you have a certain amount of persistence, but that's also limited. So 30 to 150, as Group Captain Rao brought out, unusable zone. 160 is the minimum altitude for one orbit to take place. 180, about 3 orbits. 200 kilometers, about a day's operations, about 15 to 16 orbits. 250 kilometers, about a week's operation. This is unboosted, unpropelled, natural deorbiting lifetimes of satellites. 300 kilometers, about a month. 350 kilometers, about 6 months. 400, about a year. 500 is where it reaches about 5 years of natural orbital life. 100 years. 900 kilometers, 1,000 years. Geostationary is eternity. So that's the impact of density in the lower altitudes and how rapidly it varies, and which is why most of your sustained LEO operations are 500 kilometers and beyond. So we have above 160 is the orbital zone, where it changes from aerodynamics or aeronautics to astronautics. And the manner in which a spacecraft may sustain itself in the atmosphere changes. It's now based on gravity and not by propulsion. And propulsion is an adjunct to help it sustain on, in its station. It's just for station keeping or minor variations. So now we have, if I'd like to give it names, that 50 kilometers and below, starting from about 20 kilometers, I'd say, to about 50 kilometers, we can call it non-orbital near space. That continues right up to 160, but we don't know how to use that zone. Above 160 is where we have orbital space, but the lower bands of that are still very, very prohibitive in terms of the density. On WhatsApp, I got a meme the other day. It gave the definition of poor. You're poor when you have too much month left at the end of your money. So near space is like that. Near space is where you have too much density left at the end of your engine power. Right? And therefore, from 160 to about 400 is where we may possibly quantify as the near space zone, above which normal orbital things are reasonably self-sustained. Even within this, from about 160 to 250 is a hard zone. Too much density, too much perturbation, there are a lot of things. Beyond that, it eases a little, but still high. So even here, we could have probably brackets like 160 to 250, 250. Now this is entirely going by the dynamics of running a spacecraft there. Having said this, let me get on with the advantages that near space gives you. Very rightly brought out by Samir, the major advantage is in cost, and that translates to higher capacity, higher capabilities, larger numbers, and over a lifetime, the cost reducing, so higher revenue. So commercially, if you're looking at it, higher revenues, in all other ways, lowered cost of operations. So in these two slabs, let's talk about the 20 to 50 kilometer zone, which is a balloon zone. Very, very different dynamics, technologies, and ways of exploiting it. And then you have the second zone, let's say 160 and above to about 400, which is your satellite zone. So astronautic zone, but it cannot be free fall alone. It needs to be helped out with thrusting. So it's an area in which it's called VLEO, generally speaking, very low Earth orbit. VLEO requires sustained or frequent thrusting depending on the altitude. So the balloon zone is something that is starting to be looked at, and it is maturing very rapidly. So let's go with the balloons first. I'll talk about the advantages, disadvantages, what are the technological challenges, and the industry people here, the startup and the students. These are the things that we need your attention on. And then so what might be the enabling technologies? also the application. So in balloons, the main thing, of course, is cost. It's a fraction of what you will have for fixed wing aviation or for satellites. The preparation, the logistics, access to materials and fuel, all of that is much, much easier. The fuels are available, and there are a variety of fuels that can be used. Operationally speaking, if you take the zone above 18 to 20 kilometers and beyond, it's above most of the weather. So it's not disturbed by the perturbations that normally happen in the weather zone of the atmosphere. There is some wind, but the wind effect is very, very low. So station keeping is not that great a deal. However, you require the right kind of basic propulsion systems to keep it in place. Or in case you want it to patrol, you want it to be navigated, then accordingly. The line of sight zones that you get from that kind of an altitude far surpasses anything that you can attach to the ground. So if you are at about 20, 21 kilometers, you get a line of sight to the ground of about 500 kilometers. So from, roughly speaking. So we are talking about something like, 7.5 lakh square kilometers of territory can be within your line of sight. Imagine the advantages to communications and applications based on communications. Right? And if you were to go, skim the horizon to another, blimp or balloon or airship, high altitude balloon out there, 1,000 kilometers plus. So imagine that as a radio relay, maybe laser link for communications. Imagine a grid of such standing out there, each one displaced by 800 to 1,000 kilometers. In about a dozen of them, you'll cover the country. And you have a standing grid, a communications grid in near space, in parallel to whatever you may produce terrestrially. So there's the kind of power it has to give you at a much lower price point. There are several challenges and a few disadvantages. One, of course, the endurance of balloons as of now is still, Samir spoke about, the 90-day kind of a challenge and all of that, and that would be beautiful to have that, something of that power. But right now, it varies from the order of a few hours to a few weeks. The globe has been circumnavigated, by the way, in 19 days, 42,000 kilometers, okay, in a single balloon. So that has been proven. So persistence and endurance is a bit of an issue. Propulsion and fuel storage. The longer you want to be there, you'll need to have these available to you on board. Robustness and reliability, very important for the military. So you can't have those latex sheets bursting or something like that. You need materials that are strong and reliable enough. Platform stabilities could be an issue for certain payloads. So you would need to have technologies that transcend this or mitigate it. And then, of course, navigation station keeping is not that big a job, but yes, you would require engine power to do that. So the challenges, really speaking, are the ability to sustain your aloft position. So that's partly the propulsion and keeping the balloon aloft part. Solar power, rotorcraft maybe, I don't know, Samir. Solar powered, very lightweight rotorcraft may be another way to do this. Solar panel skins. So Samir once again touched upon, bendable, flexible solar panels. That's the technology that we need to break. Unless you can contour them to the shapes that are required, and grab energy from wherever you can. And if you're able to do this successfully, then your ability to generate energy goes up exponentially. And then, of course, the material science, the skin, latex, all of that. Okay, so these are the challenges, and these are the enablers that we require. There are certain technologies that have been used. Zero pressure balloons, super pressure balloons, valved balloons, which adjust the internal pressure so that the typical anomalies that take place do not take place. Those are technologies that we need to break into. Let me come to the Velio portion. This is as much as the balloon thing is concerned. Okay, one concept on the balloons part. Sometimes they're called stratostats. They're blimp-shaped ones. And HAPS has been touched upon, high-altitude platform stations or platform systems or pseudo-satellites, whatever you might want to call it, but HAPS. There is also a concept which is called geostationary balloon satellite, GBS. It's been tried out. So essentially, you have a blimp, an airship, with the appropriate payloads, a navigation, GPS and other things there, a small engine that helps it to do. And it basically stays over a fixed point on Earth. So what do you have? You have an atmospheric satellite. All you need to do is add the appropriate payloads to it, and there it's going to maintain position. So similarly, that grid thing that I'm talking about refers to that. In the Velio zone, again, the advantages are phenomenal if you're able to master the technology. So the impediments are only technology, nothing else. The big advantage is, all day today we've been immersed in, the seas. Today was a ocean of seas. So having been drenched in that, I'll also, I don't want to be left out. So 3 C's there. One is cost related. 2 is the competence related, which I'm talking about operational competence. And the third C is cleanliness. Let me explain that. Cost is enormously reduced when you compare, the operations, launch costs, operations, manufacturing, everything in a slightly higher zone, that is in the Leo zone. Pardon me. The swap factors, size, weight, power, all of that reduces drastically. The power requirement goes down so drastically that the power you're able to put out from 200 kilometers or 250 kilometers as against 500 kilometers, everything to do with range, is on the inverse square law. So all the growth is exponential. So the power radiated is high, so you can either use smaller components and lesser power radiated, or you can get more bang for the buck. The link budgets come down drastically, uplink, downlink, the losses and that part. Smaller payload sizes, smaller size of the craft itself, much higher signal to noise ratios. Right? And the radiation hardening requirements go down drastically because it's at the lower end or beyond the lower part of the Van Allen belts. So the rad hardening part, so a lot more of Khot's components can be utilized, reducing the cost even further. So these are the kind of advantages that the Velio, zone gives you. There are disadvantages, of course, because you are at a lower altitude. Your cover, your footprint is automatically reduced. So just the geometry of it. Your communication windows when you're overflying a ground station or in communications with it will get reduced. So your data rates have to be appropriately higher. So there are mitigating technologies for sure. There are restricted elevation things. And the revisit time also, because because of the reduced imprint, even if you tilt the craft to point the payload, the amount that you can cover is less, so the revisit is also impacted somewhat. There are some aerodynamic perturbations which do take place at these altitudes because there is still, like we said, some air there. And therefore platform stability and the stability, especially when pointing, could be an issue, but there would be ways to mitigate that as well. One major atmospheric problem in this area is the presence of atmospheric oxygen, which is highly corrosive. So you require some kind of materials and coatings to mitigate that part. So these automatically point us to the technologies that are required. How do I get rid of this?
Telling your time is up, right?
I said it myself. But I didn't know how to get out of the Chakravyuh, sir. So the enabling technologies for the Velio zone. One, sustained propulsion, right? So obviously we're talking electrical propulsion. Also for the HAPS and the GBS and the balloon technologies. Reduction of drag, very, very important. So we need some kind of coatings to reduce the drag. And the shape of the Velio craft is not going to be like your normal satellites that you see. At 500 kilometers and thereabout, the satellites that you have are boxy, non-aerodynamic kind of things with solar panels sticking out in pretty grotesque shapes. These ones are going to have to be streamlined to reduce the drag. So they're going to look like cylinders. There could be plates, discs, aircraft or arrowhead shapes and that kind of a thing. There are some concepts which have already flown. In fact, all the way from 2009. The power chains will have to be worked upon. So these great advantages, if you have to milk them, you need to work upon how you're going to get the solar panels working, high capacity batteries, and to be able to utilize it. Communications, laser links, all of that will have to be developed to truly extract things out of it. Materials, and of course optics and radio frequency as well as LiDAR kind of payloads for SSA work. Let me come to the applications quickly. On the both, whether on the balloons as well as the Velio aircraft, applications are largely parallel to each other. There is of course the Earth observation, surveillance kind of thing. You can do surveillance skywards, that is SSA, or spacewards for SSA, skywards for the air situation thing, because you are sitting at pretty good, imagine the balloon sitting at about 18, 20 or maybe 30 kilometers altitude and looking at the airspace with phased array radars and so on and so forth. Or on the ground, that's also possible. Electro-optical IR, kind of payloads. Now IR is going to have an enormous advantage when it is doing skywards work because the atmosphere isn't there to obscure it. Communications is where the whole story is. ISR is naturally seductive because there are photographs and things to see and so on and so forth. and they're distracting. But the real story lies in communications and how you're able to exploit communications. So wide area sectoral, broadband internet, let's say over a HADR zone or over areas that are shielded, over the Himalayas, over areas, island territories where you don't have the normal things. Put up apps and you have that cover. Radio relays, laser links, all of those are possible. Imagine doing drone traffic control from the sky, no shielding. SSA work, I already spoke about. On the civilian side, of course, a lot of science and technology kind of a thing, meteorological, weather observations, sky observations, astronomy, sub-millimeter astronomy, all of these are possibilities at a very, very cheap price. There's also the whole area of countermeasures, squarely in the military domain here. So, RF surveillance, ESM, ECM, directed energy stuff, all of these are possibilities with much, much better performance because you're outside the atmosphere attenuation zones. Now imagine this in particular, there are 2-3 areas that I would like to highlight. One is the BMD and hyperglide vehicle defense. The trajectories of HGVs, the way it's been practiced, are very, very difficult for the current ground-based radars or the pickup because of the altitudes at which they fly and the velocities at which they fly. So a BMD or a HGV defense grid can be created based on HAPS and VLEO F. Similarly for HISIS, VLEO ideal because the resolutions go up phenomenally just by reduction of height. Some of you may know that the company Planet, they brought down their SkySats from 500 kilometers to 450 kilometers to improve resolution. So the resolutions grow up phenomenally, and right now there is this plan called Stingray by a company called Earth Observant International, and they have a 60 VLEO constellation plan which will give out 10 to 15 centimeter resolution imagery without sweating, with small mirrors. So that's the kind of advantages that we're talking about. Let me quickly touch upon the integration part. Integration has to be over 3-4 different areas. One, civil military integration. You cannot have it compartmentalized. You may have firewalls, you may have bulkheads, but you need to have a common database for civil military. Whether it is for police work, whether it's for military work, whether it's for commercial work, the data that comes is useful to everybody, and we've got to integrate because there are different people running different portions of it. There has got to be integration vertically across different altitude bands. So there is terrestrial sensors, there are airborne sensors, there are high altitude sensors, and then you go into the balloon zone, and then you go into the VLEO zone, and then you go into further satellite zone. The data that comes from each one has got a different strength and a different weakness. So we've got to put this together to form that composite mosaic of capability. Each one has to work to its strength. That's the way to do the integration. We have to look at the endurance of each of these. We have to look at the repeatability, like a sortie fashion. What Samir also mentioned, where you can replace the balloon, bring it back, replace it. So sortie fashion kind of a thing, or call it repeatability, call it replacement. So that is the kind of integration that we need, for which it's going to be an institutional effort. It has to be a national approach. Until we get all the players on board, it's not really going to work well. That's what I have. Thank you for the additional minutes, sir. Thank you very much.
Thank you. Thank you very much, Khot. Now, I'll certainly not repeat any of what you said. And we have 5 minutes. I think we started about 5 minutes late. Yes, please. We may take some questions from the audience. Mike there, please.
My question is to AVM Khot. Sir, please don't take it amiss. I have worked in HQ-IDS as Principal Director of Strategy and Concepts and Doctrines. Sir, whatever you enlightened us with, but basically doctrinal tenets, little bit of strategy, concepts, definitions. Now this Space Command and erstwhile Space Cell has been in existence for almost over a decade, if I am not wrong. So what is stopping the DSA? And now it is all poised to become a defense command or whatever, in bringing out a detailed doctrine on space, and if not on space, at least inner space. Most of the tenets brought out by you are very relevant, very germane, very pertinent, especially for the academia, for the intellectuals, for the industry, for the private players, public, government servants, lawyers, etc., etc. So what is the delay, sir? It doesn't take too much time in making a doctrine. I've made a joint doctrine in 6 months. Thank you so much.
Thank you very much for your question, Commodore Schlegel. The space doctrine is very much under construction right now. We have already given out the first version a year and a half ago. Take 2 of it after the initial observations came have been put together, and right now it is in the system. The situation in space is such, compared to the other domains, that the other domains evolve at a relatively, because they've been established for a long time, they're relatively stable, and the doctrinal concepts have been worked and evolved over several 100 years of war. When it comes to space, the domain itself is relatively new. The technologies which impact it are undergoing a revolution as we speak. Not that technology truly alters basic doctrinal principles, but even understanding of space, how one may utilize it, what are truly the characteristics in terms of operational exploitation of space, is an evolving story. And even between our first take and our second take, there were some pretty fundamental changes that happened. So it's very much, space strategy is being written, space doctrine is being written, it is being processed within the system.
Yeah, okay. 2 questions, please. Yeah, okay, yeah.
Thank you for the wonderful set of comments to all the panelists. My questions are regarding simply some of the inherent vulnerabilities with high altitude balloons or high altitude vehicles in general. Especially with balloons, we know that they have a tendency to sort of drift despite our best ability to control them. And if we consider sovereignty as an aspect, then the applications, considering the risks of your high altitude balloon drifting, and your adversary could very well use a medium range ballistic missile to take them out, then to what extent should we actually be backing when we know that a more persistent a more significant investment in space technologies can give us the same similar capabilities but for persistently longer term? Thank you.
Thank you for the question, Pranay. Very simply, vulnerabilities exist in every solution that you can find. Will not ask the balloons to do what it shouldn't do, which is why I talked about a matrix of capabilities to be built and integrated so that each one is played to its strength and we keep it out of its weakness zones. So the whole thing comes down to, if balloons are likely to drift, don't let them drift. There are tethered balloons for at lower altitudes. There are free drifting balloons which are intended to drift around and gather data, and there are others which can be steered. So one of the technologies that I spoke about was actually the propulsion required to keep the balloons on station. Okay. So the development that we need is where we can have a relatively stable, navigable balloon systems which can either stay in the same positions or patrol where you want it to patrol or navigate along routes that you want it to go along. So that's the way you keep it out of trouble. It's very much open to be, but then depending on the altitude, if you're able to take it up to 30-35 kilometers, there isn't a weapon that can touch it.
Right? Hi.
Just one add-on. At the same time, your point is pretty much there. Google Loon had to cancel this program, and one of the facet was this also, because they could not hover at the same point. The propulsion and the flight control and GNC which they were using, they could not overlap, a proper mesh or a constellation. So this was also one of the reasons why that program was cancelled. But of course, we learned a lot from that.
Hi, this is Arindrajit Chaudhary. I straddle both sides. I'm a professor at IIT Bombay, and I also have a startup called Inspacity. So I think just an observation, AVM Khot covered both sides. He batted for both. Samir spoke very strongly, championed the case of HAPS. I mean, I wanted to champion the case of VLEO satellites as well. I felt that provided we have refuelability and the technologies are figured out. So I'm a propulsion person. On both sides, I have worked with monopropellant engines to keep the HAPS platforms on air without any air at all. And then I figured out that IC engines fitted with several stages of compressors, not just a single stage, almost 5-stage compressors, which can be miniaturized to a degree to fly together, offers very good solutions instead of just solar. I'm sure the team has looked at it, just confirming. And that is for HAPS. On the other side, for VLEO, provided air-breathing propulsion can be figured out at an electric level, I think it then becomes just atmospheric oxygen becomes the main enemy beyond that. So if that is figured out, I feel a constellation of VLEO satellites developed cheaply and then brought out at that level would be a trump card in some way. Yeah, that's to play devil's advocate to Sameer's side because there's nobody on the other side. Yeah.
Last question, please.
Mr. Sami, I have a question for you. Like the development of the drone, what you're looking for, 20 kilometers at the end. So what is the payload you're looking at? Like Zephyr Airbus gives around 5 kg of the payload. And it has a wingspan of 25 meters. So what is the payload weight you are looking at in your development?
So first is right now the focus is on the platform itself. But the final platform, what the Indian Air Force envisages, the payload should be about 30 to 35 kilometers to cover the northernmost latitude, which is about 37.5 degree north, flying at those altitudes. That is around where the sizing of the platform will be done. So 30-35 kgs. This will cater to a mix of all payloads. But of course, this gets us to the point, this also is very challenging. One way which everybody across the world is exploring is to get the low Earth orbit satellite payload tech down to the stratospheric levels. Why? Especially for CubeSats and, medium-sized sats, which are about 100 kgs and less. Those payloads, if they can give you about a meter from, let's say, 600 kilometers, will give you centimetric kind of precision when you get it down to 20 kilometers. So that is the approach which is happening all across the world. Yeah.
Thank you. That answers my question.
Thank you very much, ladies and gentlemen. Please join me giving a big hand to all the panelists. Thank you very much.
I'll request the esteemed panelists to kindly stay back with us for just a moment more on stage. Meanwhile, I'll request Sri Anil Prakash to kindly join us. But before we close the panel, may I take the pleasure of requesting Mr. Sudhir Gupta, former Secretary TRI and Board Member SIA, to please join us on stage to give his closing remarks.
Good evening, ladies and gentlemen. As we come to close of the first day of our session, I want to present my appreciation for the esteemed VIPs, General Anil Chauhan, CDS, His Excellency Australia's High Commissioner in India, Mr. Pradeep Green, Dr. Subbarao Pavluri, President SIA, Padma Shri Dr. Sailesh Nayak, Director NLAC, former Secretary, Ministry of Earth and Science, Lieutenant General PPS Pannu, Chairman Space Committee on Defence SIA-INDIA, and AVM Sanjay Bhatnagar, Officiating Director, St. Jude's. Firstly, I am pleased to announce that a memorandum of understanding between SIA-INDIA and the Space Industry Association of Australia has been successfully formalized. This landmark agreement emphasizes a significant step towards enhancing collaborations and fostering mutual growth within the space industry. Against the backdrop of DevSat 2024, where India showcases prominence in both defense and space sectors, this MOU lays the foundation for a modern and forward-looking industry. Now to sum up the discussions which we had today, our event featured from 4 panel discussions, each offering profound insights and strategic outlooks into the future of space and defense. The session on mesh intelligence multi-sensor payloads and analytical platforms delved into the realm of military remote sensing, exploring advanced topics such as AI integration and multi-payload spacecrafts. The next session was on space-enabled precision and deep barriers, where the esteemed speakers explored the pivotal role of remote sensing in precision battles and tactical decision-making on the battlefield. The session Collaborative Frontiers Synergizing the Defense Innovation Ecosystem uncovered valuable lessons that will shape the future landscape of defense innovation initiatives, fostering collaborations and pushing for the boundaries of technological advancement in national security. Redefining Aerospace, Near Space and Space Sovereignty, the last session. Here the experts discussed the evolving dynamics of air and space, delving into topics such as ISR and operations in near space, discussions on drones, UAVs, balloons, and innovative solutions. I invite you to remain engaged and participative as we move on through day 2 and day 3 of DevSat 2024. Together, let us delve deeper into the intricacies and space exploration, defense technologies, and emerging trends as we collectively shape the future of these technical critical sectors. Stay tuned for an enriching and enlightening experience that promises to inspire, inform, and ignite the new pathways and progress. Thank you. Thank you and good night.
Thank you, sir, for joining us on the days to sum up the day's proceedings. And we take this opportunity of thanking the esteemed panel, the esteemed chair, for being with us in this session. It's been an enlivening discussion. Thank you for taking us through with it. So, ladies and gentlemen, before we call it a day, please do remember that the action starts tomorrow bright and early in the morning at 9:30 a.m. sharp. So, looking forward to having you all there and some more. So, please don't forget to join us in time. And of course, a gentle reminder, if you haven't registered yourselves for the War Games session, please do so now. As you can see on the screen, the sitting arrangement with the color codes, orange, green, white, silver, everything is in display. So we had earlier demarcated different groups. There'll be volunteers, of course, to help you all. And I leave this session with the same question that I was asking last year also. This is addressed to, of course, the session chair and all the esteemed speakers as well. When can, as an event manager, I start advertising that your wedding garland will be delivered through a drone?
Long time.
Or maybe your wedding will be advertised in the near space.
Near space.
Please do let me know, and please do join us back tomorrow for many more such interesting sessions as well as questions. So have a wonderful evening ahead. Thank you, and see you all tomorrow. Good night.